Good afternoon, everyone. I'm so excited to be here today at BSides NoVA, presenting you a quick presentation on single sign-on attacks and misconfiguration. Before I get started, I wanted to say that this talk is intended to be completely open, so all of the sources I use are all open source. All of the references will be at the end. These slides will be on my website sometime later. I'm recording this talk and going to post it, so please share it around. Everything inside, like I said, open source and only opinions of my own. A little bit about me before we get started. So I got my career started several years ago doing full stack web development. Spent a little bit of time doing embedded systems. Nowadays, I spend most of my time doing the cool cloud stuff, right, that you can't do in your home lab. That's awesome. But where I got the interest for this talk really came when I was in college. I was a member of the Penn State Dance Marathon, specifically on their technology committee. And this is one of the largest student organizations in the country, right? We have about 25,000 people involved in various ways. And so, like, if you think about it, right, this is a picture during the event that I helped run. And every single of the 25,000 plus people in this audience need to have information about their identity, right? Like, what should they have access to? What role management should they have? And there were 25 of us volunteers on the technical committee. Like, that is all volunteers, full-time students. We didn't have the staff to do like a help desk, reset someone's password. So the solution to that was good integration with single sign-on. All right, so no matter who you are, I'm hoping you can get something out of this talk, whether your career is more on the offensive side with the red team, more on the blue team side, looking for IoCs, anomalous detection. I'm also going to touch on some compliance techniques. And then also the yellow team. This actually wasn't a term I was super familiar with. I'm just going to use it to refer to the kind of thing that I am a cloud engineer, right? On the engineering side, talking about, taking lessons from the attacks I'm going to show and turning them into lessons about secure system design. Okay, so real quick, in case anyone in the audience is not familiar with single sign-on, we're going to do a crash course. So at the top here, we start with our identity provider. This is far and wide the most important term when we're talking about single sign-on, because that's your source of truth for everything you could ever want to know about your users, right? That's where attributes like first name, last name, email are stored. That's for credentials like, password, maybe a two-factor token, that kind of thing. That information will be stored in your identity provider. But then at the bottom are your service providers. So those are the downstream services, right? A great example is, let's think of Google, right? Everybody here probably has a Google account. You sign on with Google's identity, the single sign on, and you can use that to talk to many services, right? You can go to Gmail, you can go to Google Drive, you can go to Google Cloud. You don't have like a separate username and password to go to Gmail and then a separate username and password to go to Google Drive and so on. You just have one centralized single sign on for all three. One of the main benefits to this is that like we can spend a lot of our time securing just one aspect, right? We don't need to worry about, okay, if Gmail's database leaks, that's not good, but at least they don't have all our passwords, right? So we can focus our time on that compliance level for the identity provider and don't need to spend as much time for the service providers. But also, we empower our users by only requiring them to remember one set of credentials, right? We all know that it's more dangerous to need to have users remember 1,000 passwords because then they're going to reuse passwords, have weak passwords and such. So it's awesome if we can just have our users remember one password. And that's, again, like really where the idea of single sign-on comes in. So some common single sign-on protocols that you probably have heard of before. The most popular is probably OAuth, right? OAuth 2.0 and 2.1, which was released somewhat recently. I'm actually not going to be focusing on that for today's talk. Instead, I'm going to be focusing on the Security Assertion Markup Language, or SAML. This choice was really made out of that it's very easy to see what's going on under the hood with SAML. I'm going to be doing some live demos where we're directly inspecting the SAML payloads as they go between different services. And so there's a lot of similar concepts with OAuth, but we're not going to be covering that in this talk. Okay, so what is SAML, right? Well, the key letter in SAML is the A for assertion, right? So the whole idea behind SAML is that you have this payload that is declaring something to be true, right? I know this is technically a misuse of the Farquaad meme, but I still imagine like a king going out and saying, "Oh, I assert that this is the truth," right? This document, this XML document, represents some set of true conditions, right? And so the flow for how SAML 2.0 authentication works is we start with some kind of initializing event that's called a SAML request. I'm going to go through the flow for that in a minute. And then our identity provider will actually print out the right term for it is a SAML response. But throughout this talk, I'm going to be referring to it as a ticket from time to time to go along with the golden ticket theme. But that SAML response contains all of that information that you would want to know about your users, right? So information like first name, last name, user ID. It's not going to contain your credentials because your services don't need them, but also the role information. So your admins probably have like an administrator role, and that will be encoded within that SAML response. Okay, so we're going to go through the flow. I know you've probably seen these vertical timeline diagrams before, and they're really intimidating, but they really are the best way to describe what's going on. So I'm going to hold your hand through it. Don't worry. But we're going to start by looking at a non-single sign-on situation, right? So on the left, we have a user, right? You can think of it really more like your web browser. And on the right, we have the combined identity provider and service provider. So it's like if you went to Gmail and you just had a Gmail username and password directly, right? No single sign-on. So we start with an anonymous request, right? We open our browser afresh, and the downstream service doesn't know anything about who we are, right? So they respond with some sort of credential entering page. I'm going to call it a login page for the purpose of this presentation. You enter your username and password in this login page. Next, the user responds with their credentials, right? They type in their username and password. And then finally, the service responds with secure content. That's pretty straightforward, right? We're going to take this now and build in the single sign-on part. So we're first going to start with the sort of simpler situation. There's two different types of flows. The first one is identity provider initiated flow. So in this scenario, you can think of, we're going to start by looking at like a dashboard that you log into and then can talk to services from there. So a great example, right? If a lot of corporations have an Okta dashboard as their like landing page for their intranet, and that's an example of IDP initiated flow. So we start with exactly the same scenario, right? The user connects to, their Okta dashboard, puts in their credentials, gets return the secure content. But then, and this is where we build in the single sign-on part, the user expresses some intent to authenticate to some other service, right? So again, to use the Okta dashboard as an example, maybe you have like webmail that you click a button on your Okta dashboard and then it redirects you to your webmail. That is the user sending a request saying, I am intending to authenticate to this downstream service. The identity provider then prints that ticket, prints that SAML response with all that information encoded as a redirect back to the user. And now finally, we're over to that service, right? In the middle here, we have that downstream service. I said webmail before as the example, where the user actually just redirects back from the identity provider over to that service provider and hands over that SAML response. And finally, now the service provider trusts that the SAML response is legitimate and serves back that secure content the user is logged in. Now, hopefully looking at this diagram, you're instantly thinking like, what happens here, right? Like clearly you can't just as the user submit anything to the service provider. There must be something special about the SAML response, the SAML payload that the service provider knows that it can be trusted, right? Knows that it's trustworthy. We're going to get to that in a minute. But I'd like to go to another example of the flow as well. This is actually probably the most common flow that you'd see. So we're going to forget about like the Okta dashboard and instead go back to the Gmail example, right? I want to log into Gmail. So I go to mail.google.com. I start with that anonymous request. But now, because the service provider like Gmail isn't going to authenticate me directly, it needs to redirect me over to the Google single sign-on in order to perform the SAML request and response flow. So the service provider will generate a request, redirect me over to the identity provider. And now we have the same flow that we saw before, right? So the identity provider will return us a login page, we enter our credentials, and we get redirected with that response. And now it's exactly the same as the identity provider initiated flow because we take that response, we send it over, the client, the user sends it over to the service provider, and then we're logged into Gmail, right? Great. But once again, I want to call out, no matter which flow, they both have this interesting step that is, how does the service provider know to trust the SAML response? I'd like to make a connection, like if you've ever read a math textbook and you look at a proof, it'll often say like every single step in the proof is trivial, But there's one key interesting step. Like, this is the step that makes the proof interesting. And I will say the same thing about this. Like, this step that the service provider knows to trust that SAML response is the interesting step. Okay, so let's do a real demo looking at some actual SAML payloads. So the smarter people doing presentations today did video recordings of this. I'm going to try to do it live. So we're going to start over here with a sample app. The code for this sample app is open source. I just threw this together using a popular SAML library. But I'm going to pull up my DevTools to make sure I have a recording of all the network events and log in. So when I log in, some of you may recognize this as Keycloak. It's a very popular open source identity provider. It doesn't really matter that it's Keycloak in this example. What matters is that we are doing the service provider initiated flow here. Because I started in the service, I'm now redirected over to the identity provider. And we can look at that SAML request payload that I mentioned before. So over in our DevTools, it's a very simple request, just sends over this payload. So let me just copy this. Okay, the next tool I'm going to show, as you can tell by the DevTools, right, that payload is encoded. You can't just human read it, right? But it's only encoded, not encrypted, so we can just decode it to actually look at it. And this tool that I'm showing here, the SAML Investigator, is something I built myself specifically for this talk. Like I said, it's open source. I'm going to be leaving this website up for the indefinite future, so please feel free to use it in whatever engagement or educational environment you'd like to. But this SAML, this allows us to paste in that SAML request payload. And you can see here, it's really simple. It's like 10 lines of XML. The only things that are really important here are this issuer that tells me, hey, I'm Gmail, or I'm this SAML demo that I'd like you to authenticate. And the other is this, it's called a solicitation ID that I will come back to in a minute. Let's keep going. So we have the SAML request. Let's look at the arguably more interesting payload, SAML response. So I'm going to log in as my user with an extremely complex password. Okay, great. So we logged in, single sign-on is working. Fantastic. Before I take a look at the payload, I want to quickly point out that I made this sample app to have these printout of all the things the payload is passing to it. So you can see we have a UID and we have role information that comes from the SAML payload. And now let's take a look at actually where that is. So in my DevTools, I can find this ACS payload, and that stands for Assertion Consumer Service. It's a bunch of jargon, but the important thing is that that's where the SAML response payload goes. Hopefully you can tell it's much, much larger than the SAML request was. But I paste this in here, and here we go. Here's the SAML response. There is this signature body at the top that we're going to dive into a lot later in the talk. But there's a couple things I want to point out in the response here. So a really important one, I apologize if this is a little bit hard to see. Let me make it a little bigger if I can. This is my username, right? That is just encoded within this payload. And then if I scroll down, you can actually see all of these roles, right? So I have this like manage account, offline access, UMA, authorization. All of that is just down here in the attributes, right? So as I mentioned before, everything that you could want to know about that user identity information is all just encoded within this payload. All right, back to the slides. Okay, so it's time to think like a red teamer. Let's really like analyze that step, right? Whenever the payload, the SAML response, the ticket goes over to the service provider, what actually happens, right? So there's two ways that the SAML response is kept secure, right? We can't just generate one out of nowhere via lifetimes and via signatures. So the lifetimes are really, really simple. It's just a timestamp to let you know whenever the response was generated, and a solicitation identifier, which means that for a service provider initiated login, that you didn't just make this up, right? That this was a fully initiated flow. But the signature, of course, if you're familiar with signature cryptography, is the real way that we verify, this was generated actually by who we thought it was, right? Only the identity provider will have its private key. So only the identity provider can generate a valid signature for this payload. It also helps with integrity, of course, because if we modify the payload but keep the same signature, it's not going to work. So I want to quickly just look at what those actually are, right? So the solicitation ID is up here in the subject confirmation data. So you can see it's this big long. I'm using a one login library, so it doesn't have to start with one login. But in this scenario, if you remember, the request actually matched that same ID. So that tells you, that provides the service provider the lineage between whenever it initiated the request and now here's its response. But the other thing is all kinds of timestamps, right? So we have this condition not before, not on, or after. It's really self-explanatory, right? It's just saying, hey, if somehow we've gone back in time, this SAML payload is not valid. If it's way in the future, this is valid for 1 minute configured by default. We're not going to let this continue. This is an invalid payload. And of course, the signature up here at the top, it's just a giant blob of base 64, but it is of course the RSA signature of the whole response payload. Okay. So how do we defeat these mechanisms? Again, trying to really brainstorm, think like a red teamer. So a couple of these are really easy to defeat. The expired timestamps, well, let's just remove the old timestamps from the payload that we're crafting and put in new timestamps. That's not very interesting. The solicitation identifier is actually also really easy to just you can just get a new one, right? Send an anonymous request to the service provider. It will give you back a valid SAML request with a valid unused solicitation ID. So neither of these are really interesting because they're very easy to bypass. But the signature, right? We have good crypto. How am I going to possibly get past the signature? I'm not going to be able to defeat the RSA cryptography scheme, right? So let's think again. How does the signature verification work? So, of course, it's the service provider's job to check that the signature is good. The service provider has knowledge of the identity provider's public key. It will analyze the signature, make sure that both the payload matches and that the signature was issued by that public key, right? So pretty indefeatable. Well, what if this just doesn't happen, right? What if the service provider is misconfigured so it just doesn't check the signature? So let's do our first attack demo. Where I'm calling this a misconfiguration attack because I'll explain later, your SAML environment should not be configured this way. But we have this response, right? I haven't gone into the other features of the SAML investigator, but this tool is actually built specifically to perform these types of attacks. So if I scroll down here, I hit next, we're going to come back to these other fields. I'm going to hit this print button to print a new payload. And what this does for me is do those couple steps that I mentioned before. It replaces it with a new timestamp, and it also replaces the ID, which is a randomly generated one. So you can see issue instant, what is it, 18/18/01? That's exactly 10 seconds ago by now. So if I click this, let me first make sure I'm logged out of here so you know that I'm logging in legitimately. Next, submit. Uh-oh, I just logged in successfully. In case you didn't catch that, let's do something a little more malicious. I don't care to log into myself, right? I know my credentials. Let's try to log in as someone else. So I can actually just go in here and edit the SAML payload. So I'm going to hit reset to make sure I get a new ID and a new issue instant. Well, let's see. What if I change my username to noah.admin, and then I change one of these roles to be the admin role? Now, whenever I submit this payload, I will get logged in. Okay, so I actually made a little mistake with how I did the username, but it's fine because you can see this role admin, right? Still got added to my account completely illegitimately. And now, of course, I have the admins only hack the planet button, and I'm in. Thank you. Okay, so you might have just seen me do that, and this might be your face right now. How could we have misconfigured this so severely, right? This pretty much completely defeats our authentication mechanism. Well, I have good news for you. There are ways to mitigate this. So the first thing I want to point out is actually the SAML specification itself, right? The link here goes to the Oasis SAML security guide, which is the first party, original source for the SAML specification. And I have printed out here the most relevant part of that security guide. You notice how it says here, it is highly recommended that such a system be used. I wouldn't call it highly recommended. I would call it required, right? Because otherwise you can easily defeat the SAML authentication mechanism. I'm sure that the team at Oasis wrote it this way so that you could have certain implementations that didn't require it. But in a real web production environment, you need to be checking these signatures. So not just highly recommended, required. Also thinking about the compliance end, so I will say if anyone can find something better in a compliance framework, please tell me afterwards because I'd like to update this talk. But in all the searching that I did for any compliance frameworks, the closest thing I found was in a STIG on the DISA application security development STIG on the latest version as of this talk has a control that talks about these SAML assertions. But you'll notice the language says that you must sign the SAML assertion. Okay, great. We signed it, but it doesn't say anything about actually checking the signature, right? So this control is good, but does not mitigate this attack. So you could be completely compliant with every SIG that I have knowledge of and still be susceptible to this attack because you're misconfigured. So really my point is it's up to you, right? It's up to you to go and check on your systems and make sure that you have this configured correctly. If you're a developer, please make sure when you're developing SAML integrations that you are requiring the user to set this up. An example I'd like to give, this is a screenshot from Slack. Actually, if you try to integrate SAML into your Slack workspace, you are required to enable signature checking for at least the response or the assertion. That's good. That's what we want to see, right? Thank you, Slack, for configuring this correctly. I also want to call out that even though, like, to be clear, this is not a vulnerability, but it is a weakness, right? And so there's no sort of CVE associated with this, but there is a CWE associated with this, right? The idea it's a common weakness to not properly verify cryptographic signatures. And so I really want to call out the CWE 295 because if you want to go to work on Tuesday and be like, hey, I need to spend some time checking on this, here's how you can justify it to your boss. Say I was checking in on CWE 295. I'm also gonna throughout this talk connect it back to TLS, right? Because like one of the things I think is interesting about how SAML signatures and encryption works is it's very relatable to TLS because like the underlying crypto is exactly the same. And so I'd like to call out that if you've ever seen this, right, curl-k or like in Python request.get with verify equals false, that is exactly the same thing, right? You are telling the client, the HTTP client, that you don't want to verify that the certificate you're receiving is valid, right? So I know that there's some additional complexity to actually exploiting this in the wild, and I'm going to touch on that later. But I want to call this out, right? This is still severe. In your production environment, you should never see an example of one of your developers setting verify equals false or doing curl-k, for example. Because again, it's the same thing, right? You're still opening yourself up to ignoring signatures. But okay, we're going to come back to this, right? What is another thing we could do? Let's say our service provider is configured correctly. It is checking the signatures. Is there anything else we can do? We're really trying to brainstorm. So let's look back at the SAML security guide. And I included this additional paragraph because right below what I highlighted before, it mentions, hey, you're guaranteed that the message hasn't been altered unless the key has been compromised. So, okay, let's make an assumption. We're gonna perform the Golden SAML attack right now. This is the main part of this talk. So I said key compromise, right? How would someone possibly compromise your private key? Well, this is the KeyCloak administrative portal. In here, it might have signed me out, so let me refresh the page. I want to call out that I'm not looking at any infrastructure right now, right? Like I'm not like inside of the cloud or SSH to a machine or anything. All I have is this web portal, but yet I'm still able to mess with the private key here. So I'm going to just generate a new private key. Don't worry, the private key is on the screen right now. It's also a bespoke one I generated for this. So let's generate a new private key and copy it. Okay, and then we can enter it into the KeyCloak key configuration. So I can just add my own generated key in here. I'm just going to call it NoVA. I'm just going to paste it. Great. I need to run a quick restart on my service. And now that I've loaded this key into KeyCloak just through the web environment, I have told all of my services that, hey, this key that I have control over is a valid signing key for this identity provider. The reason the services have knowledge of this is because there actually is this metadata service. You can see now there's not just one key here, there's two. There's two public keys. This is the like quote unquote legitimate one that was initially created by Keycloak, but here down here is my newly created one, right? So that's not great. That I can just by having that Keycloak access, I'm able to now set it to include a key that I can control. Okay, the other thing I need to do before I continue this demo is to make sure that I actually turn on signature verification, because otherwise this won't make sense. So I'm going to log back in legitimately as my user and turn on signature verification. So now whenever I try to perform exactly the same attack again, you'll see that it'll fail. Let me reset the payload, submit. And now you can see that I get an invalid response, right? This is good. This is what you should see if you have an invalid signature or no signature. But there might be an extra feature in this website that you can actually paste in a private key. So I didn't do this before, but now I'm going to enter this key that I just created, paste that in there. Next. I'll go ahead and print a new payload. And real quick, I'm planning on adding this to the website later, but I can look at the dev tools and it should... Oh, it didn't print out for me. Well, we'll see whenever we go to the new tab. We'll get that signed payload. So there it is. It works. Just because I had control over that key, now I have access to the same attack. Thank you. And once again, I can do exactly the same thing, right? I can edit my payload. Let me log out. I'll edit my payload correctly this time, so my username shows up as NoVA admin. Admin. The trick is I need to set it here as well, admin, and then I'm just going to change this role to say admin. Here we go. We're in as NoVA admin. So once again, like I didn't know the username and password for this administrative user, but I was able to just print my own response because I took control of that private key. So that was a lot. Let's do a quick summary of what just happened, right? So I was able to have some form of compromised key, right? In this specific scenario, it was because I had access to the Keycloak web portal. I could mess around with it. Didn't need any more access than that. Didn't have to look at any underlying infrastructure. I was able to combine that with previous SAML response information and create my golden ticket, right? To be clear, that was the Golden SAML attack. There is a different attack called the Golden Ticket attack. Sorry, you fell for my clickbait title. It's not exactly the Golden Ticket attack. But another thing I want to call out about that is, like, sure, the name for this attack is Golden SAML, but we didn't just get a golden ticket. We printed a golden ticket, right? We have a ticket printer. We can print as many of these responses as we want. I have the picture of Jerome Powell printing out all the currency in my head. So, like, this is not just running on my machine, right? I could go hand it off to someone else if I wanted to give them administrative access too. Another thing that makes this attack really powerful and why I want to talk about it is because it's really hard to audit, right? Because the reason this attack works is that the service provider cannot distinguish between a maliciously crafted, a counterfeit SAML response payload and a real one. So in all of your logs, it's going to show up exactly the same. Like, really, the only way you could see it from that perspective is if you're doing some advanced, maybe user activity monitoring, you see someone's logging in an unusual time, but otherwise your logs are going to look identical because, again, the whole reason the attack works is that the payload is identical to what would correspond to a real response. There also maybe is an argument to be made that if you have really fancy correlating of logs, you could see, like, well, I didn't find any logs in the identity provider to show me that the service provider was supposed to be issued a response. But I think it's still worth mentioning because in many scenarios, like especially that Okta example, right? You might not be able to like go inside of Okta's infrastructure and look at all their logs. That might be like, I need to make a phone call with someone type thing. Not something you could like send an automated alert for. But there still are ways we can defend against the Golden SAML attack, just not from the perspective of the service provider, right? So the real lesson here is to protect your private key. Right? A lot of what I find interesting about talking about this Golden SAML attack is that, you know, we call it the private key. Everybody talks about like, oh, you shouldn't leak your private key. But this is a very succinct example of why your private key needs to be very locked down, right? A couple of ideas, right, for how to implement this. There's a million ways you can do protection over your private keys, but I wanted to throw out just a couple ideas here for the point for the purpose of this presentation. A great one is to make the key difficult to recover, right? So if you notice in Keycloak, those default keys are almost unrecoverable. Like to actually read those keys, you'd have to do some fancy stuff in the Keycloak database. You're going to leave a huge fingerprinting trail, right? Who's running these weird queries in these tables in Keycloak? Another idea is to keep it behind audit, right? A lot of newer people to the cloud might be confused why we use these secret management tools, right? But it's all about auditing. Like when I put my private key into an AWS secret instead of just, a task definition, I make it so someone has to take an explicit action to break the glass and view that private key, and that will show up in my logs versus, I don't know, it could just be in an environment variable somewhere, and I wouldn't know, the list of people that have ever looked at this key. And then a good mitigation, of course, is just to make sure you have limited access. Like, I really like to point out that there's this feature in Keycloak because, as a reminder, like it might not just be your system administrators that can go in and SSH into your environment. It could be people that you gave Keycloak admin to, right? Maybe you have a help desk that needs to manage users in Keycloak. Don't give them access to that realm management because you'll give them the ability to mess with those keys, right? There is also some like IoC/anomaly detection we could try to do on the blue team side. I put the red color here as well because for the red tiers, this might show up if you're trying to do this attack somewhere. So you should look in your logs and see what a bad SAML payload looks like, right? Because there's almost no situation where you should ever see a bad SAML payload comes in. The only one that I can think of off the top of my head is sometimes a user will legitimately send an expired payload. Sometimes your laptop might go to sleep, and whenever you open back up your laptop, it'll resubmit the same one. So that's something valid. You probably don't want an alert for that. But something like on the screen here is my logs. I give an explicit log that say I got an unsigned SAML response. That will never happen, right? In the real world, that is an instant sign that something is wrong. Someone's trying to mess around with your system. Coming back to the TLS connection, right? So once again, like a lot of times when we're talking about key compromise, you might think that there are these additional protections in place. Like let's say I had the private key for the certificate for people.com. I can only do so much with that. But just remember, right? Like, especially if you're doing a targeted attack, there's still a lot of ways that you could use that malicious key, right? If I set up a DNS poison network, if I whip out a pineapple and show set up a network called Mason or BSides NoVA free Wi-Fi, maybe I know that one person here will go to a very specific website for whom I've compromised their key, and their browser will just accept it because it'll be a valid signed response at that point. So, thank you all for your time. In summary, the main things I want you to take away from this talk: please check your configuration of your SAML service providers. Please make sure that SAML response signature verification is turned on. And if you're building a system that requires SAML integration, make sure you don't allow your users to turn it off. It must be enabled. Protect your private keys, right? Make sure that no matter what you're using your private keys for, whether it's for SAML or maybe it's for TLS or for SSH, make sure they stay under lock and key. They shouldn't just be open to the public somewhere. And finally, keep using single sign-on, right? I don't mean to scare anyone away from using SAML with this talk. Like I said at the beginning, single sign-on is a great way to remove the barrier for so much work for your IT staff to make sure people have the right access and the right groups and the right roles and everything. So please keep using great single sign-on tools, but just use them carefully, just like anything. We're going to do a quick lightning round of other topics that I was not really able to cover in this talk. So when I was developing the SAML investigator tool, I had to rewrite the attack in JavaScript instead of I originally wrote it in Python. Crypto in JavaScript is very fun, but it turns out that Chrome and Firefox serialize XML differently. It's very strange. I thought it was a Chrome bug, but they are in fact both spec compliant. There is also a sort of new-ish topic in the single sign-on world called single logout, which is the companion to single sign-on. It's been around for a while, but the reason it's more of a hot topic is because there's more and more attack vectors coming out about how people could, your user thinks they're logged out, but because it wasn't integrated with single logout, they're actually still logged into the identity provider, and then their session gets taken over. There's also some more interesting stuff with replay attacks. Specifically, so I called out those like timestamps, but there's also a one-time use element that can be found in the response. That's a little dubiously implemented across frameworks that I've seen. I put links to a couple. The Python 3 SAML toolkit, it implements it interestingly. So that's an interesting vector to look into. Maybe some further research required. Client signatures is also a feature of SAML that I didn't touch on. So just like I focused on server-side signatures, right? The identity provider signs the response payload, but actually you can also require your clients to sign the payload. I think this is, again, something I want to look into more. Not super relevant for this talk because if you're using IDP-initiated login, there is no client SAML request, so it's not relevant. You can also completely encrypt your SAML payloads but in both directions. I find that this is not super common because the SAML framework was written to not require to be on top of TLS, right? Because you could use it for other things besides logging in your web browser. So maybe you're not behind TLS and you don't want to just send it over plain text, so you do encryption. I would not consider that like a mitigation for these attacks, but it is something you can use. And then finally, key rotation. So like we all know that everyone wants to rotate your certificates. The certificates have a very defined lifetime. We're getting them shorter and shorter down to 45 days or lower. But nowhere in there do you ever need to rotate your private key, right? You could theoretically keep using the same private key to generate a CSR and get a new certificate forever, right? And so I don't have a strong opinion about this, and that's why I'm not spending too much time on it here. Because on one hand, with respect to the Golden SAML attack, that could help you to prevent, your key being compromised. If you're only using it for a year or 6 months, then it only can be valid for that much time. But also at the same time, you could argue that defeats the whole like unrecoverability aspect. Clearly, if I have to regenerate the key or rotate the key, I'm interacting with it in some way that maybe would open it up to a greater audience and greater service for compromise. Thank you all again for your time. I'm honored to be here. It was great to share a little bit about single sign-on and the Golden SAML attack with you, and have a great rest of your day. If you're interested, here's some of the references that I use in for this talk. Like I said, all the code is available on my GitHub. I'm going to be making this into a blog post and the slides on my website. It's not there yet, but it will be soon. So please get in touch. Feel free to chat about single sign-on or anything identity. Thank you.